Today we are going to discuss derivatives involving trig functions. So remember the basic trigonometric relationships. The sine x is 1 over cosecant x, or cosecant x is 1 over sine x. Secant x is 1 over cos x, or cos x is 1 over secant x. Tangent x is 1 over cotangent x, and cotangent x is 1 over tangent x. Cotangent x is cos x over sine x, and or cosecant over secant x. And tangent x is sine x over cosine x. Sine square x plus cosine square x is equal to 1. That's another Pythagorean identity. Sine square x plus cos square x is equal to 1. We can divide everything with the cosine square x, and that would give us tan square x plus 1 is equal to secant square x. We can also divide everything with cosine square x. That would be 1 plus cotangent square x is equal to cosecant square x. Okay, derivative of trigonometric functions. Memorize these derivatives. Today in this video, I'm only going to use these derivatives. I have another video of proving these derivatives. All these can be proved very easily using the limit definition of derivative. Derivative of sine x is cosine x. Derivative of cos x is negative sine x. Derivative of tangent x is secant square x. Derivative of cosecant x is negative cosecant x cotangent x. Derivative of secant x is secant x tangent x. Derivative of cotangent x is negative cosecant square x. Keep in mind all the trig functions with the co-c in the front, their derivatives have negative sign in the front. We also know the two special trig limits, sine h over h when h goes to 0 is equal to 1, and 1 minus cos h over h when h goes to 0 is equal to 0. So let's start looking at the examples of using these derivative rules for trig functions. So derivative of 3 over x plus 5 sine x. So I can rewrite the function as 3x to the power negative 1 plus 5 sine x. That derivative turns out to be negative 3x to the power negative 2 plus 5 cosine x. X squared plus 2 cosine x, that derivative would be 2x plus, actually minus, because derivative of cos x is negative sine x, minus 2 sine x. 4 tangent x minus 3 cotangent x. 4 tangent x minus 3 cotangent x, that would be derivative of tangent x is secant square x. Derivative of tangent x is secant square x, and derivative of cotangent x is negative cosecant square x. So 4 secant square x plus 3 cosecant square x. The negative and negative becomes positive. 4 square root of sine x. So I'm going to pull out the 4. 4 is a constant, and do the derivative of square root of x and sine x, and use the product rule over here. Product rule says first function times derivative of second function plus second function times derivative of first function. Derivative of square root of x is 1/2 x to the power negative 1/2, which is 1 over 2 root x. So this turns out to be 4 root x cos x plus 2 sine x over square root of x. Next we have x squared over cosecant x. This is going to be a quotient rule here because we have a quotient. Cosecant x, low in the denominator. Lower term times derivative of higher term times 2x minus higher term times derivative of lower term. Derivative of cosecant x is negative cosecant x cotangent x. A little bit cleaning up, 2x cosecant x plus x squared cosecant x cotangent x over cosecant x squared. Looks like the cosecant x is a common factor between numerator and denominator, and I'm left with 2x plus x squared cotangent x over cosecant x squared. One of the cosecant x cancels, and final answer turns out to be 2x plus x squared cotangent x cosecant x, and that's our derivative here. Next, number 6, we have cos squared t. Later we will learn other techniques of evaluating this derivative, but right now I'm just going to write it as a product of cos t and cos t. So first function times derivative of second plus second function, which is cosine t, times derivative of first, which is negative sine t. So it's going to be negative sine t cos t minus sine t cosine t. That will turn out to be negative 2 sine t cosine t. Let's look at another example. X e to the power x cosine x. So here we have 3 functions, so I'm going to keep the first 2 as it is, derivative of the third one, and then first and third as it is, derivative of second one, and then second and third as it is derivative of first, which is 1, and that would be the derivative here. There's no like terms we can combine, so we'll just leave it like that. Next, we have three functions now again, first, second, third. So first function, second function as it is, and derivative of the cos x would be negative sine x, so that would become sine square x, plus x cube, cos x as it is, and derivative of sine x is cosine x, so that would become cos square x, plus 3x squared sine x cosine x. And that's the derivative in this case. Next, we have derivative of cos square x plus sine square x. We know cos square x plus sine square x is Pythagorean identity, and that is equal to 1, and derivative of 1 is going to be 0 because 1 is a constant. Derivative of 1 is 0. Next, we are going to find the slope of tangent line to the given function at t is equal to pi over 3. Okay, so to find slope of tangent line, we need two things. We need a point on the tangent line, which is going to be pi over 3, and sine pi over 3 over 1 plus cosine pi over 3. And we also need the derivative y prime. That's going to be the slope of tangent line. So let's go ahead and start by finding the derivative, slope of tangent line. So y prime comes out to be, we'll have to use the quotient rule here because we have a quotient of the function. So y prime would be 1 plus cosine t squared, 1 plus cos t times derivative of sine t, which is cosine t, minus cos t times derivative of sine t, which is cosine t. Lower function times derivative of higher function, derivative of sine t is cos t. Okay, and here it is going to be higher function, low d high, minus high d low, and derivative of cos x is negative sine t. So that's going to be negative sine t. And this turns out to be y prime is cosine t plus cosine square t plus sine square t. The negative and negative will become a positive, divided by 1 plus cos t squared. On the numerator, I'm left with cos t plus 1 squared. When you're adding two terms, the order does not really matter. You can switch the order. So changing the order doesn't really make any difference. I would be able to cancel one of the factors. So y prime turns out to be 1 plus cosine t, which is 1 over 1 plus cosine of pi over 3. Y prime, when t is pi over 3, at t is equal to pi over 3, y prime is going to be 1 over 1 plus cosine pi over 3. And we can make a quick table of the trig functions. Cosine of pi over 3 is 1/2. So cosine of pi over 3 is 1/2. 1 over 1 plus half, which is 1 over 3/2, and that's 2/3. Now I do need to find the point sine pi over 3 over 1 plus cos pi over 3. And I'm just going to use a calculator, or you can go ahead and plug the values from the table here. If you are using a calculator, make sure you're in the radian mode. So sine pi over 3 divided by 1 plus cosine pi over 3. 1 plus cosine divided by 3. That turns out to be square root of 3 over 3. So my point is pi over 3 root 3 over 3. Okay, so we have the slope m, we have the point x1, y1, which is pi over 3 comma root 3 over 3. Now we are ready to write equation of tangent line. Equation of tangent line would be y minus y1, which is y minus y1, y minus root 3 over 3 is equal to m. M is 2/3, x minus x1 is pi over 3. Y minus root 3 over 3 equals 2/3 x minus 2 pi over 3. And we can go ahead and add the root 3 over 3 to the other side to isolate the y. This is the equation in the point slope form here. And if we want to isolate the y, we can write it in the slope intercept form. Let's check out another example. Find the equation of tangent line to y is equal to f of x is equal to cos x at x equals pi over 2. Okay, so we're looking for equation of tangent line at x equals pi over 2. Let's start by finding slope of tangent line, which is m, same thing as y prime. The derivative of cos x is negative sine x. And negative sine x at x equals pi over 2 is going to be negative 1. And the point is going to be pi over 2, comma, cosine of pi over 2. Cosine of pi over 2 is 0. We are ready to write equation of tangent line, which is y minus y1 is equal to mx minus x1. x1 is here, y1 is here, and your m is here. So y minus y1 is equal to mx minus x1. Turns out to be y is equal to negative x plus pi over 2 is our equation of, that's our equation of tangent line to the curve y is equal to cos x at point x equals pi over 2. Here's another example. Calculate y double prime, y triple prime, and y is equal to tangent x. Okay, so y is tangent x. What is the derivative of tangent x? Derivative of tangent x is secant square x. So first derivative is secant square x. Okay, for this one, we do need the chain rule. So we haven't talked about the chain rule. I'm gonna skip this one for now because we do need the chain rule. Or we would have to, let's see if we can do it without chain rule. Y prime is secant square x, and I can write it as secant x times secant x. Y double prime would be the first function times derivative of second. Derivative of secant x is secant x tangent x plus second function, which is your first function, second function times derivative of first, which is secant x tangent x. So this turns out to be secant square x tangent x plus secant square x tangent x, which is 2 secant square x tangent x. I'm just going to find the second derivative, because if I have to find a third derivative, I have product of 3 terms here, and that would make it really, really long. We'll talk about chain rule, and that would make our life so much easier. So I'm not going to find the third derivative, just the second derivative here. But if you want to find the third, you would be able to write y double prime as 2 secant x, and then tangent x, and then start doing keep the first 2 derivative of third, keep the first and third derivative of second, and keep second and third derivative of first. Find the 37th derivative and 240th derivative for cosine of x. Okay, so let's first start thinking about y is cosine of x. The first derivative is negative sine x. Second derivative is going to be negative cosine x. Third derivative is positive sine x, and the fourth derivative is cosine x. So fourth derivative, it repeats itself. Eighth derivative will be also cos x, and 12th derivative will be also cos x, and 16th derivative. So you will see this pattern going on forever. All the multiples of 4, those derivatives are going to be cosine x. Back to cosine x whenever you are doing a derivative that's a multiple of 4. So if I'm looking for f of 37x, the 37th derivative, think about the 36th derivative. 36th derivative is going to be back to cosine x. So 37th derivative is going to be the next one, which is negative sine x. Now think about 240th derivative. We don't really need to calculate all the 240 derivatives, because we do know 240 is a multiple of 4. And every multiple of 4, cos x derivative turns out back to cosine x. So 240th derivative will be back cosine x. Now let's look at horizontal tangents. We've talked about horizontal tangents earlier as well. Horizontal tangent lines have many applications in calculus. You can find when the function has a horizontal tangent line by taking the derivative of function and setting it equal to 0. Because whenever you have a horizontal tangent, the slope of tangent line would be 0. Here's an example. We have looked at it graphically. Let's take an example of a sine x function. We're going to have a horizontal tangent here and horizontal tangent here, and slopes of these tangent lines will be 0. Does the given function has any horizontal tangent? Y is equal to 2x plus sine x. Let's go ahead and calculate the derivative, which is x. No, it's not going to be x. It's going to be 2 plus cosine x. 2 plus cos x. And now we need to think about, is that 2 plus cos x ever equal to 0? Or is cosine x ever equal to negative 2? That's a no, because cosine always stays between negative 1 and positive 1. It's never bigger than positive 1 and never smaller than negative 1. So no, it's not possible for this graph to have a horizontal tangent. I'm going to take care of f of x is equal to negative cosine x. Find what values of x does the function have horizontal tangent. So let's go ahead and find the derivative and set that derivative equal to 0. Is there any point where that f prime of x is sine of x? Is there any point where the derivative is 0, where sine x is equal to 0? Where is the sine x going to be 0? Sine x will be 0 when x is 0. So at x equals 0, we would have a horizontal tangent. And again, at x equals 0 and 2 pi, so all those points, we would have a horizontal tangent whenever your sine x is 0. Sine is a y value, and if you recall, your y values are 0 at y values are 0 at 0 degrees, pi over 2, pi, and then back to 2 pi, and 3 pi, and 4 pi. So all these multiples of pi, all the multiples of pi, we would have horizontal tangents, multiples of pi. All right, another example. Find the derivative of each function, 2x minus tangent x. That would be 2 minus secant square x. For the next one, we do need to use the quotient rule, but I'm going to make my life a little bit easier. I like to work with sines and cosines instead of cosecant and secant. 1 over cos x. I'll give myself more room. I'm going to clean it up. You didn't have to do that, but I think it's easier for me to think about in terms of 1 over cosecant x, 1 over cos. 1 over 1 minus sine x, which leaves me with a sine x minus 1 over 1 over cos x. So cos x, these are two complex fractions. You can write them instead of division line in the middle. We can say sine x minus 1 over sine x divided by 1 over cos x. Sine x minus 1 over sine x times cosine x. Sine x cos x over sine x, which will be sine x cos x over sine x minus cos x over sine x. We can get rid of the sine x and sine x, and it turns out to be cos x minus cotangent x over sine x. Cos x over sine x is cotangent x. Now we can just do the derivative here, f prime of x. The derivative of cosine x is negative sine x. Negative sine x, and derivative of negative cotangent x is going to be a negative, which will become a positive cosecant square x. And that would be it. Here's last 3 examples that we are going to look at. Y is equal to sine x and tangent, sine x times tangent x. So first function times derivative of second, derivative of tangent x is secant square x, plus second function times derivative of first. Okay, a little bit simplification, sine x times secant square x plus tangent x is sine x over cos x, which would be sine x, because we can sine x over cos x times cosine x. Cos x and cos x is gone. Sine x times secant square x plus sine x. Pull out the sine x. Secant square x plus 1. Secant square x plus 1 is equal to, no, that's not the identity here. So we would just leave it at that point. Sine x times secant square x plus 1. 1 plus tan square x is secant square x, but we cannot use this identity here. If we had a negative sign there, we could mess around with it and use that identity, but with the plus sign, we cannot use that identity. Derivative of tangent x is secant square x, f prime of x, and derivative of cotangent x is negative cosecant square x. Secant square x and negative cosecant square x. Okay, the last problem we're going to look at today, I would have to use the quotient rule. 1 minus cosine t squared, 1 minus cos t, derivative of sine t is cosine t, minus sine t, derivative of 1 minus cos t would be positive sine t. Okay, which turns out to be cos t minus cos square t minus sine square t over 1 minus cosine t squared. Let's see if we can use any identities, anything else here. If I pull out a negative, cosine t minus cos square t plus sine square t over 1 minus cos t squared. All right, now this would be cos t minus 1 over 1 minus cos t squared. If I pull out a negative from here, I can write it as negative 1 minus cosine t over 1 minus cosine t squared. We are able to cancel the common factor. Negative 1 over 1 minus cosine t is what we're left with. Negative 1 over 1 minus cos t. And that's all for this problem. And we would stop here. This is our last problem. Let's check out one more. A weight hanging from a spring is stretched down 5 units beyond its rest position, released at time t is equal to 0 to bob up and down. Its position at any time t is given by the function s is equal to 5 cosine t. What's the velocity and acceleration at time t? Okay, so because we know the position function, velocity v is going to be ds dt, which is a derivative of 5 cosine t. That's going to be negative 5 sine t. And acceleration is going to be, acceleration a is going to be d square s, or we can do dv dt, derivative of velocity as d square s dt square. That would be negative 5 cosine t. And that's it. That's the end of the derivative of trigonometric functions.